Good morning to everyone and welcome to today's webinar, Optimizing Nutrient Removal in Oxidation Ditches. This webinar is part of the US EPA's Office of Compliance Technical Assistance webinar series for plant operators, inspectors, and compliance assistance providers. My name is Peter Behor from the US EPA Office of Compliance. My colleague Laura Paradise and Brendan Held of the Region 4 Atlanta office will be operating webinar. Attendees do occasionally experience technical difficulties. If you lose audio, we recommend that you close the webinar and log back in. GoToWebinar recommends using the Google Chrome browser for optimal performance. The webinar is being recorded for future viewing. A link to view the recording will be posted to our website. A copy of the presentation slides, Q&A report, and other handout material will be mailed to all webinar registrants in about a week. We encourage you to download the presentation slides now from the Handouts section. Your audio is muted, so to ask questions, select the question mark to the right side of the screen, type your question in the box, and then select Send. You may submit your questions in the question box at any time during the webinar. Regarding certificates, all registered attendees will receive a follow-up email to GoToWebinar in 24 hours with a link to download a certificate of attendance. Please look out for this email and check your spam folders. If you're watching this webinar today as a group under the name of one registered attendee, please type first, last name, and email address of all other persons in attendance in the Q&A box in order for everyone to receive a certificate of attendance. EPA cannot guarantee the acceptance of certificates by your organization, nor can certificates be provided by viewing the webinar recording. I'm very pleased to have Grant Weaver with us today and for the next 4 webinars from January, February, March, and April. Grant is licensed wastewater operator and professional engineer. He holds a BS in biology and an MS in bioenvironmental engineering and completed postgraduate studies in environmental toxicology at MIT. Grant has visited and worked with the staffs of over 150 North American municipal wastewater treatment plants to realize significant improvements in nitrogen and phosphorus removal. You can find his full biography in the Handouts section now. With that, I turn over to Grant. And Grant, thank you for helping us out today.
Well, thank you. Let me get this all booted up the way it ought to be. I think we got it now. And thank you, Peter. Thank you, Laura. Thank you, Brendan. And thank all 700 plus of you that are listening in. In particular, thanks to those of you in the Midwest who it's lunchtime, and those of you in the Mountain West where before I run out of steam here, it will be lunchtime. So thank you all for tuning in. We're going to do our best to make this a valuable time for you and worth your time. As Peter just mentioned, we've got a series going here. I don't know how I got EPA talked in to allow me to do a series, but we're going to talk today about oxidation ditches, dialing in nitrogen and phosphorus removal in oxidation ditches. Today's going to be more of a opportunities, kind of a quick overview. Well, let me get into what we're going to do today. Let's talk about the series first. And then in February, be doing a similar webinar on sequencing batch reactors, SBRs. One more time, we'll do it in March, and we're going to talk about conventional and extended air activated sludge treatment plants. And then I'm really looking forward to this 4th one in April. The last few years, I've kind of been working through my head this idea of going from permit compliant to wastewater excellence. And I want to do some brainstorming with all of you that are interested to participating in that. The first 3 are going to be really focused on operator level. And then this last one be more operator and management, regulators, academics as well. So today we do a quick review, talk about biological. I think I got to do a little context, can talk about nitrogen removal, phosphorus removal. I don't know, spend 15, 20 minutes talking about that. And then bring in the different oxidation ditch design concepts. Pretty interesting to me. I made a count. I've been to something like 30 oxidation ditches that I've worked with. And you would think that the racetrack would be kind of one design. Well, there's not. There's a lot of different designs. So we'll talk a bit about that. Then the fun part, I think, for all of you will be the case studies. And the case studies, I've got 5 of them queued up. And if there's time, we'll get through all 5 and talk about their treatment plants, kind of what they're doing that's operating them a little. In all 5 of these, they're operating them a little differently to a lot differently than they were designed, purposefully, and kind of cause and effect for what their operational changes have made. And I hope that'll create some questions, discussion in the plant for those of you who are running oxidation ditches, may want to consider some changes in your day-to-day. Maybe it'll get some interesting discussion started. Speaking of discussion, I'm going to have breaks along the way where I'll put a slide up that'll say questions and comments, but I'm encouraging Brendan Held and Peter Bayor, who are both kind of monitoring your comments and questions. They're welcome to interrupt me anytime. So I always take that as a compliment that the more interruptions I get, then the more interest there is in what I'm saying. All right, a disclaimer. Here's my view. EPA is doing us all a service by hosting these. And further, EPA's allowing people like me to speak without a lot of review and evaluation, kind of whitewashing or scrubbing to make sure that what I say is all okay. So it gives me some freedom. Now I'm going to try to make it also it's fine, but any opinions or conclusions, they're mine. I haven't run them by EPA. They're not buying into these things. So if something stupid comes out, blame it on me. If something smart comes out, thank EPA for that. That's my disclaimer. And then the acknowledgments, man, I could do slides and slides. Visiting, as Peter said, over 150 treatment plants. A lot of people have taught me a lot of things. Today, I'm going to share the lessons from these first 5, Gene Miracle in Basor, Kansas, Eric Miller and Corey Fox in Chinook, Montana, Ronnie Kelly, Tom Graham, and John Buford from Cookeville, Tennessee. Nice article about their work in TPO magazine. Similar, Great Bend had a nice article in TPO magazine. Jason Cawley, Ruben Martin, April Batts, and James Gott. And Oneida, the last case study, Greg Podge Birchfield, Chad McDowell, and Greg Overton. And then all these state folks who really have supported the work, promoted the work, encouraged people to take a chance and try operating their plants differently. So today we'll share some success stories. And if you have questions about things that didn't work, ask away. Well, we'll be honest about that. All right, let's start off with some background on nitrogen removal. Kind of hard to talk about what we've done at the what we've done. See, I do that. Whenever good things happen, I throw the we in. What the operators have done, some of the good things they've done at the plants for nitrogen removal without giving a little foundation. So those of you who are really 100% up to speed on the ins and outs of biological nitrogen removal, bear with me for the next 10 minutes, if you would. We'll get on the other side of that and we'll do it over again for phosphorus, a little briefer, get deeper into phosphorus, I think, in the next session. All right. There's really a 2-step process for nitrogen removal. One is to convert the ammonia. I wrote it up here as ammonium. For any of you chemists or lab geeks, The pH we deal with, most of the ammonia is technically ammonium, but we convert an ammonia form of nitrogen to a nitrate form of nitrogen, and that happens in an oxygen-rich environment. Now, much of the nitrogen actually goes into the sewer pipes as organic nitrogen, but with no process control, the vast majority of it converts to ammonia. And what doesn't convert to ammonia? I've been doing this for a few years. I don't know a lot of process control to help move organic to nitrogen to ammonia. So I skipped that step. That's not a process control step. The two process control steps, we're going to start with ammonia, and you can see we're going to exchange those H's for O's, which means we're putting oxygen in there. Not only do we not need a BOD for the bacteria to grow, really don't get much ammonia removal in a treatment plant until the majority of the BOD is treated, is depleted. So the soluble BOD is taken out of solution, it's used to grow bacteria. Once there isn't much BOD left, those bacteria slow down, gives the opportunity for the ammonia removing bacteria to grow. Good process control tool. If you're removing ammonia, you're pretty confident your soluble BOD is in real low numbers. The bacteria are sensitive to pH and temperature. Having said that, a couple things. One is plants in Montana and northern New England, all around the country, are getting year-round ammonia removal. So that concern of being able to get ammonia removal in low temperatures seems like we're moving past that. pH is pretty critical. I'll talk about that in a minute with some of as I put some illustrations up here. But what I found is most plants, once they dial in ammonia removal, except for those once in a while upsets that occur, or during a major storm event when the hydraulic retention time is just plain too short, ammonia removal is fairly constant. It's the second step that most operators that I've worked with have a hard time keeping anywhere near as consistent as their ammonia removal, which is kind of ironic because the bacteria that convert the nitrate to nitrogen gas are hardier bacteria. They thrive in pretty much the opposite environment. They need a lot of BOD, and if there's free oxygen available, bacteria won't be bothering to breathe the oxygen off the nitrate. They'll be breathing the free oxygen, the dissolved oxygen, and we're not going to reduce the nitrates very much. You know, animals want to live, and they'll fight to live, and if there's no free oxygen, they'll fight to find oxygen where they can, and they'll find it on the nitrates. And I said animals, and I'm not sure if bacteria are considered animals anymore. 50, 60 years ago even, I don't think they were. So anyway, living organisms, let's do that. All right, so it's a two-step process. Let's go through the two steps kind of quickly. First step is ammonia removal. I start with my little ammonia chemistry thing there, NH4. We're adding some oxygen. Oops, the hydrogen ions go into solution. As they do, that makes the water more acidic. If there's a soft water like we have in New England or on the West Coast, there may not even be enough buffering, and that pH will start to decline. It can even decline to a point where it becomes toxic for the bacteria that remove ammonia. But in harder waters, like in the Midwest, where there's stratified rocks, typically there's enough buffering capacity to keep the pH high enough. First step, one family of bacteria will convert ammonia to nitrate, and then a second family, nitrite, and a second family will convert it to nitrate. Now, what I've seen, and let me get my little marker here, if I can push on the right button. Looks like I got it. Sorry, folks, hold on. Laser pointer, that's what we're looking for. So this first step, the pH can drop pretty significantly, and this step will continue. My experience, and it's fairly limited, so if any of you have more information, please type it in. But a magic number I've seen is 6.45. As long as the pH is above 6.45, it'll support complete conversion. If it's 6.45 or below, you can get a lot of nitrites and very little nitrates. Most facilities that remove ammonia have a nitrite concentration that's less than 1, less than a half, less than 0.5 even. But if the pH drops, this number can increase. Too much nitrites, a couple problems when it interferes with disinfection if you're using chlorine. Another one is it's kind of toxic and makes for unhappy mixed liquor. All right, the second step. Now we got to get rid of this nitrate we just made. All we did was change clothes. The nitrogen's still there. It's still soluble form for total nitrogen that we're now looking at in our waterways in the permits. We haven't really done anything. We just changed its form. So now we got to remove the nitrate. Boy, there's some great news about this. If you're removing ammonia, oftentimes you can save energy and get back some of that alkalinity by removing nitrates. It's going to consume BOD. Well, if you're consuming BOD without adding oxygen, that's going to lower the BOD loading on your aeration basin. This is a real benefit. So it takes, textbooks say about 5 times as much BOD. I like to see 10. So if you have about 20 milligrams per liter of ammonia that you're converting to nitrate, you're going to need 20 times 5, that's 100 to even 200 milligrams per liter of BOD. Hence the problem with the consistent removal. When the influent BOD gets low, kind of hard to get maintained good nitrate removal. Nitrogen gas is bubbled out of the water, and we want to bubble it out in the right place. Okay, we don't want it to bubble out in the clarifier. We want it to bubble out somewhere else. Doesn't really put oxygen into the water so much as makes oxygen available for bacterial growth and BOD reduction. And about half the alkalinity that got consumed in creating the nitrate is returned. So it can be a real benefit in soft water, save money on chemicals that are needed to buffer. So that's a quick overview of nitrogen removal. We're going to apply that here in a few minutes. First, I'll do a quick overview of phosphorus removal, unless there's some questions or comments that have come in and I ought to take a pause. Hearing none, I'm going to keep yapping away here. I figure Brendan and Peter know how to jump in and interrupt when the time comes. Oh, okay, let's take a polling question. So I'm going to hand it to Peter here. This is the first of, what do we have, 4 polling questions today. Peter?
Okay, the one which best describes. Okay, the poll question has been posted. Which best describes you and WWTP, wastewater treatment plant, for those of you who don't use that acronym. See the choices, please make your choice, and we'll close the poll once we get about half or more. I think there may be a question or two, Brendan. If you want to ask the 2 you marked, you can go ahead.
Oh, sure. I guess while we're waiting for the questions, the poll answers to come in, there's one question about using ORP to assess with conversion of nitrates to nitrogen gas.
What is the question about using ORP to monitor?
Sorry, yes, verbatim. Have you used very low ORP to assist with conversion of nitrates to nitrogen gas?
Oh yeah, man, that's a great question, and the short answer is yes, and the longer answer isn't that much longer. Stay tuned. Tune in next month, because next month I'm going to get into ORP a fair amount. Today I'm really hardly mentioning it, if at all, except for this. But next month, I'm going to talk a fair bit about ORP for nitrogen and phosphorus removal. Yes, I love it. I think it's a very valuable tool.
You want to ask the next one, Brendan, and then I'll go on.
Sure. I think this is a follow-up on what you're saying about making oxygen available to the bacteria. And the question is, so the oxygen is not water soluble?
The oxygen's not what?
Water soluble?
Oh, yeah, but it doesn't really peel off and it doesn't go into the environment as dissolved oxygen. It stays bound up with the nitrogen molecule. So the bacteria grab that to respire, and then it goes through the whole respiration biochemistry process. I probably could have handled that much better.
All right, we have a response that I posted for people to see. The responses: work at an oxidation ditch, wastewater treatment plant, 14%, wastewater treatment plant, but not an oxidation ditch, 22%, work for a wastewater treatment plant owner, but not at a plant, 5%, and work for a state or federal agency, 45%, and other is 14%. And you're welcome to go on from there, Brendan. I'm sorry, Grant.
Yeah, whoever, that's all right. If Brendan wants to take over, Brendan, I think they're probably tired of me already, so that would be great.
I think I just talked about fly fishing, Grant.
Oh, you're going to let me do it. All right. You know what? Almost half of you are working for a government agency, so I really want you to listen to that fourth webinar. And more than listen, let's get some discussion going. So thank you all for being a participant. Just so pleased there's so many folks dialing in. All right, let's do this for phosphorus removal. I'm not going to go as deep into phosphorus removal. I'll go deeper into that next month. But phosphorus removal, I kind of have a chip on my shoulder about phosphorus removal. I believe that our industries made this seem a lot more difficult, at least in conceptual terms. Phosphorus removal is pretty simple. One, we convert a soluble form of phosphorus. That's the phosphorus that's up here in the clear water in the settleometer. We're converting it into being a solid, and it's either happening biologically, which means it's going into the cells of the bacteria, protozoas, the organisms, or it's happening chemically and being an inorganic a conversion and creating a flock. But in either event, our whole game is to convert soluble phosphorus to a particulate. And then step two, which is what we're all paid to do that work at treatment plants, is remove the total suspended solids, the particulates. So phosphorus removal is learning the game of how to take the soluble phosphorus and making it so that it won't pass through a filter or in our treatment plant, in our oxidation ditch, so that it will settle out in the clarifier. And this is a three-step process. Any of you that have ever heard my presentations in person or by webinar, probably heard me talk about the panda bears at the National Zoo in Washington. Now, I've been to Washington. I've seen things that look like a zoo, but I've never been in the Washington Zoo. I've never seen the panda bears. That should be on my bucket list. But panda bears what do they need to eat? Most of us seem to know this. They need fresh bamboo shoots. If they don't have fresh bamboo shoots, we don't have panda bears. So they're very fussy eaters. Well, the bacteria that remove phosphorus aren't near as cute as panda bears, at least my way of thinking, but they're fussy eaters, and they eat something called volatile fatty acids. And volatile fatty acids are a short chain carbon molecule organic compound. There's, I don't know, half a dozen, maybe a dozen different types of volatile fatty acids. Vinegar is one of them. Volatile fatty acids are the acids in the acid alkalinity ratio. For any of you that have anaerobic digesters, we can call them candy if we want. So let's call them candy. So we need to prepare the right food, the candy that the phosphorus removing bacteria will eat. So that happens in septic conditions. If it was purely, truly anaerobic, right, the acid alkalinity ratio, these acids will be converted to methane gas. So we're just short of anaerobic digestion. So we got to create the food. If you work at a treatment plant that takes in septage, man, every truckload of septage, they're paying you to take an awful lot of volatile fatty acids. Also in septic conditions, we need to have the bacteria meet up. We got to bring the bacteria to the septic conditions where the volatile fatty acids are, or bring the volatile fatty acids to the bacteria in a different septic condition. And then in those conditions, the bio-P bugs, I call them, because I think phosphorus accumulating organisms is kind of a mouthful. So I like bio-P bugs better. But when I say bio-P bugs, I mean PAOs. So the phosphorus removing bacteria meet up with the VFAs, the candy, in septic conditions, and they'll eat the candy. As they do, they become energized. They don't grow. They're just becoming energized. Kind of like me at this phase of my life. I seem to keep growing, but I'm not. I'm done with multiplying. So they become energized by eating the volatile fatty acids. Happens in septic conditions. A great process control tool and very counterintuitive is the phosphorus, soluble phosphorus actually increases threefold as this happens. So a great process control tool to see if these first two steps are happening is to monitor the soluble phosphorus going into the fermenter, the anaerobic zone, the septic process where you're pre-treating your phosphorus. And if the soluble phosphorus goes up threefold, you're operating perfectly. Now the energized bacteria, now the very same bacteria, not their brothers, sisters, or relatives, or old distant friends, they need to move into the aeration tank, aerobic conditions, and mix with the raw wastewater as it's coming in. They will take the oxygen and the BOD in the wastewater to grow, to multiply, to form new bacteria. And as they do, one of the many miracles of nature is they suck a lot of extra phosphorus out of solution. When everything's dialed in, the soluble phosphorus, if you would do a settleometer in the mixed liquor, the soluble phosphorus would be incredibly low. Might come into the plant at 3 or 4 milligrams per liter. If everything was dialed in, maybe it's 0.05 milligrams per liter, maybe less, maybe non-detect, very low concentration. So unless your phosphorus numbers are crazy, crazy low, your permit numbers, I like to just focus on the soluble form, orthophosphate, and then the particulate form of phosphorus. And this overview is how we get, in general terms, how we get biological phosphorus removal. I think in my next session, there's only so much time, right? And we're trying to do a lot in one session. A month from now, I'll go a little deeper into the phosphorus removal. But meanwhile, are there any questions or comments on that, Brendan, that I should tackle before I get into the different types of oxidation ditches?
One person asked, what are septic conditions specifically?
Yeah, I'll get into that. Septic conditions would be 0 oxygen, and if you have an ORP, it'd be in the -200 or more negative, -200, -250, -300, -350, -16 gazillion. So it's a no dissolved oxygen, just short of being anaerobic. Anything else? All right, I'll keep going. Interrupt anytime, Brendan, you know that.
All right, thanks.
So there's 4 different types, at least the way I'm categorizing. There's 4 kind of categories I put oxidation ditches into. So let me go through each of the 4. One is oxidation ditch. These are the old ones, 1970s vintage ditches. I suspect there's still some being made this way, but ditches really designed for ammonia removal, BOD removal, and not much more. So it's a racetrack, the simplified racetracks. Mine here, the schematic in blue. You can see an insert, pretty fancy one that's doubled on itself. There's all kinds of shapes and configurations of these things. But what happens in here is you've got a fully aerobic conditions. You can have a horizontal rotors aerating it like in my schematic, or they can be vertical like in the photo. There can be one, there can be any number of rotors per ditch, but the wastewater travels, and this travels around and around the ditch, travels at about the speed of a walk. So if you're walking, I don't know what speed that is. That's about the horizontal speed, maybe even a little faster than some of us walk. So it goes around and around the ditch many times, because a ditch at design capacity is typically 24 hours hydraulic retention time. So until you reach design capacity, there's more than a day's retention time. So during the day, retention time at design, I should know, but I don't. I would guess many dozens of times the wastewater would travel around the racetrack, going through, as designed, completely aerobic conditions. And then there's a weir at some point, and of course wastewater comes in. As it comes in, it's displacing the contents, and then it goes out to the clarifier. So there's the most simple form. That's my number 1. Number 2, ditches that are designed for total nitrogen removal, ammonia removal, and nitrate removal, but not designed for phosphorus removal. See a lot of these now. So for this design, there's an anoxic zone, a low oxygen zone tacked onto the front of it, pretty often configured just like this. The raw wastewater and the return sludge come into this anoxic zone. There's mixers in the anoxic zone, which aren't working at the moment. There they go, we got them turned on. And as the mixers turn, they keep the contents suspended. The wastewater, you can see, travels through the anoxic zone. There's a gap, and then it goes through the gap into the main body of the ditch. The ditch is aerated. This is a vertical shaft aerator. That's what that gear is supposed to represent. Same story as that first one. It goes around and around the ditch more times than I'd care to count. As it goes around and around the ditch, part of it peels off. There's a gate right here. It's an adjustable gate. It's a very common, and most commonly. And then a percentage of that wastewater that's gone from ammonia to nitrate goes through that gate, goes into a low oxygen zone, and the nitrates, the oxygen and the nitrates breathed off, and we get nitrogen gas. You'll get bubbling in this zone, and then the denitrified, the wastewater that's both had the ammonia converted to nitrate and the nitrate converted to nitrogen gas comes back into the body of the ditch.
Hey, Grant, one question came in: are there bubblers in the racetrack?
Some of them, I'm showing mechanical aerators. Some treatment plants do have a diffused air and have bubblers in the oxidation ditch. So some, but the majority are mechanically aerated, if that was your question.
Yes, that sounds like it.
Okay, great. All right, I'm ready to go to the third one. Third one, I don't see many of these. In fact, I can think of one in Tennessee that I've been to. I might have walked through another one, but I don't think so. I'm usually somewhat alert. So this is a oxidation ditches that are designed for ammonia removal, but not total nitrogen removal, but are designed for phosphorus removal. Kind of looks like what I just showed, except you'll note that there's no in and out gates here. The wastewater comes into a no oxygen zone. The return sludge and the raw wastewater goes septic in here, so there's no return of the high dissolved oxygen water in here to bring oxygen back into it. So it's easier for this to drop into septic conditions. And then in the main body of the ditch, it's aerated. And once again, around and around the loop it goes. But it's a plug flow system. Raw wastewater and return sludge come into a mixed, but otherwise no treatment zone. The dissolved oxygen drops to very low, needs to drop to 0 for phosphorus removal, creates that candy, the volatile fatty acids in septic conditions. Bacteria breaking down the organics to create those volatile fatty acids. The return sludge is bringing back bacteria from the ditch. So those bacteria then are feeding on those volatile fatty acids. A percentage of the bacteria are. And as they move into here, they're energized. And as they're energized and they hit the DO, then they multiply and grow. And as they do, they pull phosphorus out of solution. Again, the great process control tool is measure right here and measure right here your soluble phosphorus, your orthophosphate. It's a quick test with a spectrophotometer. You can get the test done in about 10 minutes. And so you can measure what's coming in versus what's going out. And if you have somewhere close to 3 times as much going out as you have coming in, this is working perfectly. Then it's all up to monitoring this zone, and you monitor, do some settle, either monitor as it goes in the clarifier, let it settle and see what your phosphorus is. It should be very low in here when you get it dialed in. All right, we're ready for the 4th one, which is everything. So treatment plants, and we're seeing more and more of these that are designed to remove phosphorus and nitrogen. So we've kind of stacked up, put together everything. So the raw wastewater and the mixed liquor, or no, raw wastewater, forget that, raw wastewater and the return sludge from the clarifier come into this first anaerobic zone. There's mixers. There's typically more than one zone, doesn't need to be, but that's it's pretty common to see that. So it goes into the zone. So you're getting raw wastewater and return sludge and no oxygen. The goal is to create septic conditions. Goes from that zone, hit the wrong button, and then it goes into the anoxic zone. The anoxic zone is getting some oxygen as it peels off from the main body of the ditch. It's getting a more active return going through this. So that's going to, the design here is to convert the nitrates that are produced as ammonia is removed in the main body to convert the nitrates to nitrogen gas. And here you should see the gas bubbles, the nitrogen gas bubbles coming to the surface.
Grant, there seems to be a few people asking about odor issues and about the oxidation ditch, or just commenting about it being a lot of odor from it.
There's comments that there are a lot of odors, or if I haven't really noticed many oxidation ditches at all that have a lot of odors. So the odors in these anaerobic zones or these septic zones that we're talking about, it depends a lot on the water chemistry. So if there's a lot of sulfur in the wastewater, it's more likely to have odors. It's really a case-by-case basis, but I have rarely encountered too many odor problems in oxidation ditches. It's a good comment, though. It's certainly something to be concerned about.
There's another question I'll add in here, since you like to be interrupted, and I'm working on. Are there it says, are certain types of oxidation ditches better for removing nitrogen and or phosphorus depending on climate? Do you see more of one type of ditch in certain areas, regardless of which you are trying to remove?
Wow, that's a really good question. I guess I haven't thought of it that way, so I'm going to have to ponder that. But we're going to talk about the different types of ditches and how we get these ditches to do more than they're designed. That's really kind of the rest of my whole presentation here, the next 45, 60 minutes that I want to focus on.
You'll have an option to just remind people that you'll be reviewing the questions to post webinar and be responding to them in detail too.
Right. Let me speak to that. So prior to starting today's webinar, we discussed that I'm going to receive, apparently everyone's going to receive kind of the questions and comments. I'm going to have the opportunity, and I'm going to take the opportunity to respond to every single one of them. So load me up, folks. Keep me busy. Keep me out of trouble. There's the Orbital, which is really, I haven't worked with too many, 3, 4, 5 of the Orbital treatment plants. What happens in an Orbital, most cases, this outer ring, there's one of them that I've worked with that goes opposite to this, but most of them, the influent and the return sludge go to this outer ring. The outer ring relative to the other 2 rings is huge. It's like 50%, sometimes more of the total tankage. And the oxygen is kept low in this outer ring typically. So this becomes your source that creates the volatile fatty acids. And since the return sludge comes in here as well, it's where the bacteria consume the volatile fatty acids. So the first 2 steps. And then there's some kind of a hole in here between the rings, and the flow moves then. Looks like I'm going backwards looking at the way the splashes are here. So then it goes into the middle ring, which is more of an anoxic zone for nitrogen removal, and then it flows into the inner ring. There's a lot more aerator per gallon of wastewater, so these get much higher dissolved oxygen. And this is designed for ammonia removal in here, as well as for the uptake of the phosphorus. The energized bacteria multiply. But as a practical matter, it works the same as that previous example. I could have maybe made it into 5 different types, but the same biology. Yes.
Another question for you, and also I don't know if your webcam is on. You might have turned it off. But here's a question. Would there be a reason that you would use an oxidation ditch versus an aeration basin for treatment?
Well, those who've listened enough of me have heard me say that if I was to come back to life as a sewage treatment plant, I would choose to come back as an oxidation ditch. I think oxidation ditches are the easiest to work with, have the most opportunities. And the next would be the sequencing batch reactors. It's obviously a generalized statement, doesn't apply to all cases, but yeah, I really like oxidation ditches. Now, did that just lose my picture?
No. It may be on my end and not on your end, so okay. Sorry to have it interrupted.
All right, that's fine. Oh, another, we're ready for our second of 4 polling questions. So back to you, Peter.
Okay, I'm launching it. So the question is, which one of the following would you most like to have at your wastewater treatment plant? More money to spend on day-to-day needs, more better people working at the plant, a facility upgrade, more support, less interference. I don't work at a wastewater treatment plant. So Brendan, meanwhile, why don't you ask some of the questions that you have queued up, and we'll get people to listen and to respond to the whole question.
Sure. One question was, can you explain the difference between anoxic versus anaerobic? Is it just a matter of some limited DO versus no DO?
You're correct that it's a matter of certain a limited amount of DO to no DO, and a pure anaerobic zone or septic conditions, you wouldn't even have nitrates. That bound oxygen is down to an absolute minimum. So there's no free oxygen and little to no bound oxygen as well. But the questioner got it. That's correct.
Great. Thank you. When planning for phosphorus removal, how much additional sludge should a facility plan to dispose of?
Good question. I don't know. I really don't know. I'll have to get back to you on that. I'm going to make a note of that.
And while you're doing that, I'll quickly knock out another one. What is a typical mixed liquor recirculation back into the anoxic zone relative to influent flow rate?
All right, that's a great question. And I'll tell you what, I start with adding the return sludge and the internal recycle rates. And I like to see that number at 200%, twice as much as what the raw wastewater flow is, and then go from there. Many plants, and of course, we're now moving into what would be the third of our sessions that have the internal recycle where it's actually pumped back. They're going to pump back often much higher than that. And more cases than not, I've seen that brings too much oxygen back. So in the case of an oxidation ditch, the question is, how open do you have that gate that we talked about? And monitor the conditions. You monitor what the nitrates are coming out of that anoxic zone. And if the nitrates are real low, then you can open the gate bigger. If the nitrates climb coming out of that anoxic zone, then you should close the gate. And the whole dance that you're doing is to try to get the lowest possible nitrate in the final effluent. So you may want to allow, may or may not, depending on how it all plays out in your plant, you may want that gate open a little more so that it has a little bit of bleed through of nitrate. That gives you the lowest final effluent nitrate. You may want to bring it down to an absolute minimum. It's going to be something, like I said, of a dance to see what gets you the best final effluent. Hopefully that makes sense.
The response to the polling question, which one of the following would you most like to have at your wastewater treatment plant? More money, 10%, more better people to work with, 13%, a facility upgrade, 22%, more support, less interference, 5%, and I don't work at a wastewater treatment plant, so 49%, which makes sense since we have a good portion of federal workers and state people.
All right, thanks. That's the first time I've ever asked that, and just intrigued to hear what people said. So yeah, there's a lot of interest in facility upgrades, and that's what we're seeing here. The treatment plant workers, almost a little under half, said that would be their number one. More better people, very interesting. That's an honest comment, I bet. More money and then less interference. Okay, thanks for that. Is my video back on? I'm not seeing myself, but I certainly don't need to. The
No, your video is not on currently.
It's not on. Okay. Now it's on, right?
Yes.
Does it disappear now when I advance? So that'll be my next question. Did it just disappear?
Nope, you're still there.
All right, good.
You don't need to shut it off during the polling questions if that's what you're doing. So you can just move forward. Just leave it and not toggle.
Okay, all right, we'll do that. So now, how do we take an oxidation ditch and optimize nitrogen removal? There's two ways. One, we can create zones. We can create an oxygen-rich zone for ammonia conversion and an oxygen-poor zone, kind of laterally in the ditch. Another way is to cycle the air on and off. make the whole ditch aerobic, and then the whole ditch anoxic. So I'm going to give you an example of the first one where a treatment plant is designed, not designed for total nitrogen removal, was able to create these two zones. An example is Cookeville, Tennessee. And as I mentioned, Cookeville had a real nice write-up in TPO magazine just about a year ago. If you can find that, pretty nice article. Cookeville's a pretty big plant. They have a college there, and I don't think the college population's counted here. Plus, they have some meat packing industry, so they have a high BOD. So these are some pictures of the folks at the plant, picture of the magazine they were in. You can find it online. So let me tell you about the plant. So these are the big oxidation ditches. There's a teeny anoxic tanks right in here, but we're going to discount them and play like they don't exist. So big oxidation ditches. There's one ditch. There's 3 others. So there's a total of 4 ditches. Each ditch has 6 rotors. So this thing's going to keep going 24 times, 24 aerators in this treatment plant. And again, credit to Ronnie Kelly, Tom Graham, and John Buford for the work they did. They looked at that and they thought, well, how can we create total nitrogen removal? We're getting great ammonia removal. How can we get total nitrogen removal? And they tried various things, and after a few months' time, what they found, and I'm just going to go with one ditch, and the same story holds for all 4. They ran 2 of the rotors for a period of 4 hours together. So that would create one strong aerobic zone downstream of those 2 rotors. And then the whole, this one would be off, that one's off, that one's off, and that one's off. So they have a nice aerobic condition for ammonia conversion to nitrate, and then a lot of tankage available for nitrate conversion to nitrogen gas. And after 4 hours, those 2 rotors would go off and the next 2 would go on. Another 4 hours would go by and the next 2. So instead of 24 rotors running 24/7, each rotor is running 8 hours a day. So they reduced their energy use significantly because they're only operating their aeration equipment 1/3 of the time. Hopefully that makes sense what they were doing and then why they were doing it. And then here's the results. The results are their total nitrogen was pretty good. It was around 15. And then it's consistently now been down below 5. There's been, they did a lot of work on their solids handling the last year, year and a half. And you know, unfortunately, when you're doing upgrades, there's often impacts on other things. So their work on the solids handlings had a little bit of an impact on their nitrogen removal. But so they went from 15 to 5 for total nitrogen. Little bit of a drop in phosphorus as well. Phosphorus was, what's that, 1.5 parts, maybe down to 1. It bounced back up here while they were doing the work on the solids handling. So kind of a summary of what Cookeville, Tennessee found. Their nitrogen is about 5.5, was 15. Phosphorus, little no change because things have bounced back a little bit while they have construction, but I think they really did drop it from about 1.5 to 1. A lot less electricity is used. Cookeville had been thinking about the scope of a facility upgrade that they would need for nitrogen removal. I think the number was 4 million plus. They don't need that anymore. And they're saving $250,000 a year in electricity. What they did was they put timers on each of those aeration rotors, and they spent more time. I mean, I guess I should put a tag in there that they have invested brain power and elbow grease into collecting more data and analyzing. I think if you'd ask the people in Cookeville, and I think if you'd ask the people at any of these plants today and in any of my examples, it's more fun to come to work. It's more rewarding, more of a team building exercise when the staff gets together and can get more treatment out of their facilities than they were designed for. So that's my first example, an oxidation ditch not designed for total nitrogen removal, but it's getting it by creating spatially, laterally, 2 zones, a strong aerobic zone for ammonia removal, followed by a strong anoxic. And in the case of Cookeville, you could say they lucked out that they only needed to run 2 of the aerators to maintain excellent ammonia removal. It's going to be a case by case as to what the facility, what the best way to dial it in.
Hey, Grant.
Yeah.
Ah, perfect. What was Cookeville's limits for NMP?
They didn't have any limits. There's been a lot of effort in Tennessee and discussion about pending limits, so they were anticipating limits. But as far as I know, they still don't have total nitrogen limits. I know they did not while this work was going on, which, if I can jump on my soapbox, those of you who don't have limits, now's the time. How can you violate your limit if you don't have one? So now's the time to try things and dial it in before you're under the gun and on a timeline. And that's what they did, to their credit.
Amen to that. Got 2 more that are kind of related.
Sure.
When you're rotating those rotors, leaving just a couple on, were you trying to keep soils from settling out, or have you seen issues with solid settling when you do this on-off aeration?
All right. Before this afternoon, morning, noon, or morning is over, depending upon where you are, you're going to hear me talk about the benefits of settling it out. So there is some settling, and that's beneficial. Next.
Great. And that's all we have right now.
Okay, great. Thanks. So let's go to the second option. Remember I said there were 2 ways to get nitrogen removal in oxidation ditches. Oxidation ditches not designed for nitrogen removal. One was to create the zones that's faded away. Now we're going to cycle the air on and off. So let me give you an example. We're going to go to Chinook, Montana, and we're going to thank Eric Miller and Corey Fox for all their creative work. Met Eric back in 2012 when he attended a 2-day training class in Helena that I had the honor of presenting with a fellow named Greg Kidd from Montana. I mean, from Maine. Greg and I went out, and very interesting. Eric was already well into optimizing, and staff were well into optimizing this treatment plant. So Chinook, let me zoom in on the oxidation ditch here, see where I'm doing. 2 horizontal shaft rotors to aerate, designed for both of them to run all the time. Years ago, way before this first training class, Eric and staff had found that they didn't need to run both rotors to get ammonia removal. And in fact, they found that they never had to run more than 1. So with that finding, they made this one into their summertime rotor and this into their winter rotor by covering it and putting in the ability to propane heat to keep the ice from forming on the tines on the rotors that aerate. Time goes on, again, well before I had the pleasure of meeting Eric. He realized I don't even need to aerate it all the time with one. I can still remove ammonia if I turn my rotors off. So he was turning them off for 15 minutes or thereabouts at a time, installed submersible mixer because of that concern that you just raised, Brendan, that for some reason, you would think you don't want any solids to settle. So while both of the rotors were off, the submersible mixer would go on, and there's one on each side, and to keep the material going around the racetrack. So after this first class, I suggested instead of turning it off for 15 minutes, why don't you try turning it off for a couple hours? That'll allow this entire ditch to go from aerobic conditions to anoxic conditions. And within weeks, here's the kind of results they were getting from that treatment plant. Previously, through some very creative operations using half the electricity for aeration than the plant was designed, was still getting great ammonia removal, but a high total nitrogen, and then started cutting up, cycling the air on and off, and is now down around 3 milligrams per liter. I guess I should explain in my drawings or the graphs, the bar graphs are monthly averages, and the black line is a rolling average. So that's 12 months averages, kind of takes out the ups and downs a little bit. Eric tried some things for phosphorus removal, some of them being bad ideas of mine, resulted in this spike right here, one of the bad ideas. We'll talk more about phosphorus removal here in a moment with other plants. Little improvement. You can see the phosphorus is down a bit from what it had been. I've been working on that at the plant as well. So the nitrogen is now around 3, that's total nitrogen. That's not total inorganic, it's total nitrogen. Was 20 plus, phosphorus has dropped maybe half a part. No new construction, less electricity, not really so much because of the way he cycles it now, but that was evolved over the years. Put some money into instrumentation and SCADA programming. They do it remotely, so it doesn't cost them a lot of money, the programming. And they can put off a facility upgrade, certainly for nitrogen, for, I would say, forever with those kind of numbers. So there's Chinook. Any questions or comments on that? That's an old plant, it's shallow, about 6-8 feet, I think, deep, the ditch. It's in Montana, which is already cold, but it's in northern Montana, which is even colder yet. Nope, okay, moving on. One more. And I'm not gonna take my picture off but I'll hand it to you, Peter. And Brendan, after he does that, if you got any more questions or comments, we can do that, talk in the background. But Peter, it's all you.
Yeah, just posted the question if you guys would respond. And how is Grant doing so far? Too fast, too slow? Okay, great. I'd rather not comment. So Brendan, feel free to ask some of the questions.
Yeah. Do you ever see problems with filaments with these low oxygen environments? And if so, what causes them and how do you address them?
Yeah, that's a good question. What I see more often than not is less filaments. By changing the environments from oxygen rich to oxygen poor, it kind of selects against high DO filaments and selects against low DO filaments. So more often than not, we see fewer filaments. In fact, there are some plants that are designed with a anoxic or anaerobic zone. Actually, they called it a selector there for a few years. Worked with a big plant in Nashville, Tennessee. It was designed as a selector. And that selector is fantastic at removing phosphorus removal. So more often than not, I see it better. Now, often working with folks, they'll raise their mixed liquor higher than it used to be. So their SBIs, their settleometers may look different, and the sludge may not dewater as well. So there are some downsides in that way, but generally, if anything, it helps the filament situation.
Great, thank you. And you touched on another question, which is how hard is oxidation ditch waste sludge to dewater to sludge cake? Incineration plants like 18 to 22% solids and charge extra for anything under 18.
Yeah, I don't have any great numbers on that. You know, there's so many different technologies, and frankly, there's a wide range of attention that's paid by operating staff to dewatering. Here in Connecticut, where I live, our sludge is incinerated, so it's a little pricier to move that stuff around. I can't say that I have any great experience to pass along in that regard. I'm sorry.
Want to do one more question and then we'll.
Sure, I'll read them as they come in here. How does turning on and off the air affect phosphorus removal for those oxidation ditches?
I'm going to get to that in just a moment.
All right. And that's it for now. Thanks.
Thank you, Brendan. I'm posting the responses. Grant, only 1% said too fast. No one said too slow. Okay, 17%, 81% great, and 2% don't want to comment.
And if those 2% are government workers, then I don't know what to say. All right, thank you for that. That's really, that feels great. I'm glad that the pace is good. Please comment on that because we've got more of these coming and they're for you. So thank you for that. Phosphorus, here we are. Okay, as promised. So we talked about nitrogen, trying to create 2 different strategies for getting a ditch that may or may not be designed for nitrogen removal. Just maybe those of you that have them that are designed for nitrogen removal, it's giving you some things to think about. Those that aren't designed, 2 ways. Try to create a zone or try to go in and out of the 2 different environments, kind of SBR-like, which we'll be talking about in a few weeks. Phosphorus removal. It gets a little phosphorus removal. I'm hesitant to click this button because there's a lot of words coming up here. Okay, there's 3 ideas that I want to promote for bringing phosphorus removal into an oxidation ditch, not design. One is to create some septic conditions ahead of the ditch. Find a way to run your wastewater through some kind of septic environment. And in that environment, you'll create the volatile fatty acids and then the return sludge that go into that will eat the volatile fatty acids. So you create the first 2 steps in that kind of primer I did on phosphorus removal. So you create a no oxygen environment, go septic enough to create the candy, and the bacteria that are in the return sludge come into that and eat the candy. And as they do, they become energized. Again, that great process control tool, look for how much phosphorus they release. Then the second zone would be an aeration zone, which would be the main body of the ditch, which now your energized bacteria would remove phosphorus. So that's one strategy. Second one is allow sludge blanket to develop in the bottom of your ditch. I know this is radical. So if the solids settle to the bottom of the ditch and you're cycling the air on and off in the ditch for 2 or 3 hours, it's off for 2 or 3 hours. During that off cycle, you can create a septic and anaerobic blanket. It can be inches deep at the bottom of the ditch. Inside that blanket, even though the water above it and the mixed liquor may have some lingering dissolved oxygen or bound oxygen, in that very core of that blanket, maybe it'll go septic. And as it goes septic, you'll create the volatile fatty acids, and the bacteria that are in that blanket will consume the volatile fatty acids, become energized. And then when they're resuspended, they'll get back into aerobic conditions and pull some phosphorus out of solution. I'm going to give you an example of both of these. The third one, I'm not going to give you an example today. We're going to talk about side stream phosphorus removal in some of the upcoming webinars, but it applies to oxidation ditches as well. As you create septic conditions, maybe in a sludge holding tank, and then return. The rule of thumb I've found that works, good place to start. About 10% of whatever you waste, you bring it back into the ditch, and often you can create a nice healthy population of phosphorus removing bacteria and get some pretty good numbers. So let's go through first option here, creating zones. Hopefully I don't need to repeat that. So what we're going to try to do is create a septic zone. We already have an aerobic zone, so we're going to try to find a spot to create a septic zone. So our example for that is Great Bend, Kansas, and this is kind of happening as we're talking. I don't think they have a year's experience yet where they've really got it all dialed in. Great Bend, there's an article about this treatment plant also on that tpomag.com explaining kind of the work they did there. So thanks go to the whole team. There's a lot of folks involved because they did come up with some money. They came up with about $50,000. And of course that involved upper management. So it's Jason Colley, Ruben Martin, April Batts in the lab, and this fellow here is James Gaunt. He was really the hands-on guy that really babysat this treatment plant, made it all happen. So they maintain the nitrogen removal in the ditch. The ditch is designed purely to be aerobic. They created zones in the ditch. And in those two zones, then they were able to get total nitrogen, which then this plant came with an anoxic zone. So they converted that to a fermenter. They closed the gates down to allow minimum amount of flow between the main body of the ditch and this anoxic zone. And the mixers are only run about 15 minutes a day. They purposefully are allowing solids to settle in that zone. So let's show some pictures and talk through it. And then when the flow goes back into the flow passes into the main body of the ditch, the energized bacteria are removing phosphorus. All right, so as you can see, Great Bend is an oil country in Kansas. Two of my college roommates were from Great Bend. One's still living there. The oil boom kind of left western Kansas, and so they have surplus capacity at the treatment plant. They're operating one of two oxidation ditches. So I'm zooming in on the ditch, and as you can see, this is an oxidation ditch. It has a vertical shaft rotor for aeration. You can see the air, turbulent water here, so it's designed to maintain a dissolved oxygen in the entire ditch. And then there's a gate. You can kind of see the gate there. If you have, depending upon how big your screen is, it's just above to the left to my little marker. That gate's adjustable. When the gate's wide open, as the wastewater goes around the ditch, more of it would flow into this anoxic zone is what it's designed for. And this was designed for nitrate removal. This would have been my example number 2 when I did the 1, 2, 3, 4. So this is designed to have ammonia removal here and nitrate removal here. Great Bend said, well, let's see if we can get both ammonia removal and nitrate removal in our main ditch. kind of like what that Cookeville, Tennessee case study I did. So they bought, they already had a DO probe, but they integrated it with the controls on their motor, the aeration motor. They put a variable frequency drive on it and integrated it. And then at 1/10 of a milligram per liter of dissolved oxygen, kept changing the settings until they found a setting where they were getting good, consistent ammonia removal, but the DO would drop off, the dissolved oxygen would drop off on the return run sufficiently to support nitrate removal. Took them several weeks, several months to get all those numbers right, but through experimenting, they found a great setting for it. And then they closed this gate down. This is a mixer, vertical shaft mixer. It's designed, of course, to run 24/7, keep the materials in suspension. Many cases, I'm finding that folks are getting better treatment and they're saving money by turning those mixers off for the majority of the day. In Great Bend's case, they're running at only 15 minutes of a day to resuspend the material in this zone. It's allowing a big septic blanket to develop down here. In that septic blanket, we're getting volatile fatty acid development. The raw wastewater and the return sludge are coming into this basin. So the return sludge, as it moves in and through here, then the bacteria in there are consuming the volatile fatty acids. And then as they move back into the main body of the ditch, they're becoming, they multiply. As you can see, the phosphorus numbers have dropped significantly. Again, the black is a rolling 12-month average, but you can see that as they were able to get the nitrogen removal moved from using that anoxic zone to getting it set up in the main body, that they're now averaging 0.5 total phosphorus, and their total nitrogen has dropped quite comfortably as well. You can see in the past they had some very good nitrogen removal. Then they had a change in staff and they lost that knowledge base, and now they've more than gained it back. So that's an explanation for what's happened there. So Great Bend phosphorus now half a part. Can't tell you how happy the state is with their progress. The nitrogen was over 10, now it's at 6. Kansas has a target for all their mechanical plants of 10 nitrogen and 1 phosphorus. Great Bend's there. Costing about 50 grand. They're using less electricity. I don't think we've attempted to quantify it yet. Their in-house engineer said that they had anticipated that they would need to spend $6 million to upgrade that facility for phosphorus removal. So it's a win-win for everybody. Pretty happy about what's going on in Great Bend. And it all comes down to the people making this happen. Any questions or comments on that, Brendan?
Yes, quite a few. Let me try to find the one I was going to ask you first. Will the septic conditions in the blanket allow more ammonia release from the sludge?
Yeah, I'm sure it does. I'm sure it does. And there is such a thing as letting that sludge sit too long. Not only will you you decay the bacteria, and as they decay and break apart, they release ammonia. You can actually start to digest it, so you release too much phosphorus. So that's why that tool, process control tool, monitoring your phosphorus, orthophosphate, your soluble phosphorus concentration in and out of that zone is so important. If you start seeing 4 times as much phosphorus coming out of there as going in, then you're too septic. So yes, there is such a thing as going too septic.
Thank you. Now, do the VFAs supply candy only to BioPs? Can they help heterotrophs denitrify? We get a lot of septage.
Fantastic question. the bacteria that denitrifiers, the bacteria that remove nitrates, will outcompete the phosphorus removing bacteria for that candy. That candy is like the steak, and the nitrogen removing, the nitrate removing bacteria, the denitrifiers, they prefer steak to hamburger, but if there's no steak, they'll eat the hamburger. So the trick is to produce the VFAs and to produce them in a place where you can get where there's very few nitrates so that the majority of your VFAs go where you want them for phosphorus removal. And there's a lot of strategy involved in that. And this thing that I just set up or just explained, the volatile fatty acids are produced in that zone where we're getting the phosphorus removal. So it's advantageous. But yes, there are other, it's probably the favorite food for many organisms. It's very easy to consume.
Great. And there's two that are kind of related. I'm going to try and tie up into one.
Okay.
One is, can you use the collection system as the first steps for BioP? And two, how is nutrient removal affected by high DO stormwater flows through storm events? Okay,
let me do the second first. Unfortunately, high stormwater flows, particularly in areas where there's snow melt, so you get the cold water, high dissolved oxygen, low retention time, wreaks havoc with nitrogen and phosphorus removal. Depending upon, you basically come back from it after that. So big fan of regulation of permits that are being written as rolling averages, so that it allows for those bad days to happen when the storm flows come. So it's a great question. Now back to the collection system, providing some pre-treatment or some first steps. Definitely Influent that's real low in DO is septic, is going to contain volatile fatty acids. But the volatile fatty acids then need to come into contact with some mixed liquor, also in low oxygen environments. So if that septic influent, which is really full of volatile fatty acids, goes right into the aeration zone, that's the favorite food. That's the steak. And it's the candy, the steak, it's going to be eaten by everybody else before it gets to the phosphorus removing bacteria. So that's a management issue of bringing that septic waste into contact with mixed liquor in also septic conditions. And if you can figure out a way to do that, you're really going to take advantage of it and get a real boost in your phosphorus removal. Great observation.
All right, and there's a few more, but I think in the interest of time, we'll maybe follow up with those offline.
Yeah, let me do a time check, Grant. So it's 25 after the hour, and everybody knows we're about a 90-minute presentation, but Grant has agreed to go longer for another 15 or whatever minutes that we need. We've always given flexibility to the presenters to extend their time, and I think things are going well. So Grant, I just give the heads up to people that we will probably be going over a bit.
Okay. I'd like for most folks, if you can hang in for another, let me run over for about 10 minutes here. I'm going to do one more case study. And then the last case, then I have 1/5 one, but that one's kind of an extra credit. So if you can possibly hang in here for this last one, this 4th one, I think you'll find it worth your while. And then obviously anybody wants to hang in, there's nothing I love more than hearing myself talk. So I'll be here till next Tuesday talking if you let me. So the second one approach for phosphorus removal is to actually create a blanket in the bottom of the ditch during the air off cycle. And Oneida, Tennessee is finding success with this, and I've been working, had the pleasure of working with them for the last year. And I got to tell you, the staff there, which is Greg Birchfield, Chad McDowell, and Greg Overton, it's been a pleasure working with them. And Brett Ward, who works for University of Tennessee, one of the smartest hands-on technical support guys out there. There's others. There's folks in Ohio, John Van Domlin's fantastic, great guys in Montana I've worked with. There's folks in rural water that I've worked with that are really good, Tennessee and Kansas as well. But Brett Ward years ago suggested that they cycle the air on and off in this oxidation ditch. So in Oneida, for a goodly period of time, they've been running with the 3 of the 4 rotors on for 3 hours and then 3 of the 4 rotors off for 3 hours. And this rotor here is basically kept off. That rotor is nearest where the influent is. Right near that rotor is 2 submersible mixers. And the idea was that when the 3 rotors that operate on and off, these 3, when they cycle off, the 2 mixers would turn on at 100% to keep that circular motion going. They're now running one of the 2 at 50% during the 3-hour air off cycle, which is allowing some sedimentation to occur far away from where that mixer is. And when that sedimentation occurs, they're getting an anaerobic blanket in there. They're getting volatile fatty acid are being produced. The bacteria that settle down are eating them. And then when the air kicks back on, they're getting the phosphorus uptake. The state of Tennessee has loaned the Oneida staff some spectrophotometer to do in-house work, and they've been running weekly in-house soluble orthophosphate testing now for 6 or 8 months. And they historically have been running daily ammonia testing. So they're very careful about their ammonia, and they're monitoring that. Now they're monitoring the soluble phosphorus, and they're getting tremendous results by cycling these 3 rotors on and off for 3-hour period. And then they've gone from running these 2 mixers, both at 100%, they're on variable frequency drives, both at 100% during the air off cycle, to running just one of them at 50%. So much less mixing. You know, this is kind of weird for all of us, right? Now I'm telling you to turn your aeration equipment off and let solids settle, and you can get better treatment. If you manage it and you know what you're shooting for, and you monitor what's going on, in many cases, these are the kind of results you can get. All right, this is a little squirrely graph here. What I did in the black line is the average of the 3 years, last 3 years. What's that? 2018, 2019, and 2020. So I did the average of those 3 years. And then from 2021, right about here in May or June, is when they went from running the 2 mixers at full speed to only 1 at half speed. And you can see they're tracking now better than they did historically. Now, a second thing you'll notice on this graph, and it's very common for phosphorus removal, the phosphorus is higher in the warmer months and lower in the cooler months. Very, very typical. Many, I would say the vast majority of treatment plants are getting somewhat to hugely different phosphorus, effluent phosphorus, summer and winter. And here's just another case of that. Their nitrogen has been good. It's remained very good throughout. So Oneida, nitrogen's consistently around 8. Phosphorus, those summer peaks are much less than they used to be, and their overall average is lower. And sometimes these mixers, when you do the math on how much running a mixer 24/7, it can add up to some money. And I don't think I did calculate it for Oneida, but it's enough to make a noticeable change in what they're paying for electricity. So I think I have the one and final polling question. And then for those who want to stick around, we can do our extra credit. How's that sound?
Sounds good here. On a poll question for you. And if Brendan has any questions, and meanwhile, while we launch this, you guys can read it. I won't read it to you, but you guys can see it. Grant, for you, it's how can we, Grant, specifically make this webinar series better? I'll let people respond to that and let Brendan ask a number of questions.
Sure. So I think you might have covered this, but I thought since someone asked, we might as well reemphasize. But in these case studies, there is no chemical phosphorus removal going on, or is this is strictly all biological, right?
That's correct. I did not say that. I'm so glad you brought that up. Right. All of the case studies I'm using are purely biological. No chemicals for phosphorus removal.
Great, thank you. Has turning the aerators on and off had any negative effects on effluent pH?
On any effects, negative effects on what?
Effluent pH?
No, more often than not, turning the aerators off if you're not totally nitrifying and denitrifying. If you're removing ammonia but nitrate, creating that air off zone is going to actually help keep the pH up, because you're going to bring back half that alkalinity you lost while removing ammonia. So more often than not, now if you leave them off for a long time and go septic in your effluent, then that's a whole nother thing. We're not promoting that.
Right. Next question was, I see that turning off aerators helps with meeting phosphorus limits. How does this affect effluent BOD, which I think you just touched on?
Again, the same thing, and that's it's kind of subtle, but every milligram per liter of phosphorus removed, if you do by creating those septic conditions, it requires, textbooks say 25 milligrams per liter of BOD. I don't know what the real number is. I don't know that I've had any field experience trying to quantify that, but you're going to remove a lot of BOD with no air. So that's going to lower your oxygen demand downstream because there's less BOD. Huge benefits in both the anoxic for nitrate removal and anaerobic for phosphorus removal. You're ratcheting down the BOD, which lowers the demand on the aeration zone. I'm glad you gave me an opportunity to jump on my soapbox for that one.
Hey, I throw them up, you knock them out, right?
Yeah, throw me the softballs. I love it.
When you add denite to the nitrification process, do you need to change your mean cell residence time? And if so, what way?
Yeah, more often than not, you'll find all of this works better at a higher mixed liquor, which is a higher mean cell residence time. And the limit on that is going to be two things. Usually it's mostly the clarifiers. You obviously don't want to blow solids out the clarifier, so whatever they'll hold. And then secondly is what your aeration equipment can properly aerate. But rule of thumb, I would say the higher the mixed liquor that your plant can handle, as long as you can handle it in those two regards, the better off you are. The higher mixed liquor, the downside is going to be kind of overcoming your fears to know that you can manage it. And then often it'll be a little sloppier sludge. Dewatering can be a little more problematic when you have a higher mixed liquor.
Why don't we stop there, go over the poll question, do a little debrief for everybody, then we will continue on with your fifth and extra bonus option.
Sounds great.
At that point. So the response, as I close it and then push it out, more information on nitrogen removal, 19%, more on phosphorus, 22% more case studies, 44% more technical information, 38%, and less technical information, 3%. So did you catch all that?
I did.
Okay. So let me do a little update for everybody about the next coming one that you're doing, and if people need to sign off, if they're already past the bottom of the hour. But we will continue. Just let people know that your next webinar is going to be February 17th at 1 o'clock Eastern, East Coast time. We'll be using a new platform, so we're going to be having to get used to that Zoom platform, so you'll notice a different invite next time. You will look for your certificate of attendance participation, which will come in a link 24 hours after the webinar today. So look for that link in order to find the actual certificate and look in your spam folders. With that said, also the handouts, if you haven't seen the other upcoming for March and April and moving forward, they're listed. Laura has uploaded in the handout section the handouts for today's presentation, the bio, and also the list of upcoming webinars. So please download those if you haven't seen them. And with that said, Grant, I think we can move ahead with the rest of your presentation.
All right. So here's our extra credit here. This is the tricked out treatment plant. Wastewater, Kansas, and credit goes to Gene Miracle and his staff. This is a treatment plant that has it all right? So let me zoom in a little bit on the air, on the biological parts of the treatment plant. There's two oxidation ditches. Obviously, Basor is it's a growing suburb of Kansas City on the Kansas side, and this half of the treatment plant has 3 anaerobic zones. This is for phosphorus, and then an anoxic zone, and then the aerobic zone. This side, they made an add-on to build the anoxic zone. So these two are the anoxic zones. These two are the same as this one. And then preceding it is the phosphorus removal. So this plant has the raw wastewater, and the return goes through a no oxygen zone for phosphorus removal. Then goes through, right now they are using this northern side. Every 2 years they shift. This summer they're planning to shift to the southern side. But then the flow goes through this anoxic zone. That would be the nitrate removal. And then in the main body of the ditch, they get the ammonia removal, and the energized phosphorus bacteria are pulling phosphorus out of solution. So that's the design. What are they doing differently? Well, what they're doing differently is they're doing less mixing. What they found was all the agitation in their pre-anaerobic and their anoxic was actually interfering with, it was too much splashing, too much mixing, was creating maybe a uniform top to bottom, left to right environment, but they were better off having an environment that wasn't so consistent and having lower DO zones. So I think there's a total of 7 mixers between, there's 3 in here and there's 4 in this section here. They're running now with 2 of the mixers in here, and then they're bumping the 3rd mixer every day. And in here, they're running with 2 of the mixers and bumping the other 2. So simply by turning down their mixing, you can see what it's done to the phosphorus. Their summer peaks, which have historically been, in the 3 range or higher. Now it's down much lower. I've got something in my way over here. And This last summer, they had a much lower peak in their final effluent phosphorus. BOD is always very good in this plant, and if anything, it's gotten better. Now, before I get to this, let me back up. So talking to Gene in advance of this webinar, what I've found is that many treatment plants, that part of the helps them get through the summer doldrums to take some of these tanks offline. So he's contemplating the idea of, can he run maybe partial so that he doesn't have so much retention time in low oxygen or no oxygen environments, allow some BOD, more BOD to bleed through into the aeration zone. This is the Grant Weaver theory. I don't know anybody else, any smart person that buys into my theory, but the more I go to plants, the more I buy the theory that in the summertime, I think the BOD is so low going into the aeration tank that it's actually hindering the ability to grow the phosphorus removing bacteria. So Gene's going to be considering whether he may or may not want to try to reduce the amount of low to no oxygen, let some of the BOD bleed into here, and see if that'll help him even more with this summer phosphorus removal. So the nitrogen's fabulous. The phosphorus has gotten better. Really, he's saving money on electricity, having more fun going to work, managing the beast rather than the beast managing him. And I'm hoping he's up for more nonsense and more efforts. Again, Kansas, the goal in Kansas is a total of 10 for nitrogen and 1 for phosphorus. I think he's there right now, but I think he can probably get that phosphorus a little better by taking some of those tanks offline summertime. All right, that wraps it up for me. Anything else we want to discuss? Lay it on me. I'm all for it.
If there are any last questions that Brendan wants to ask that he thinks as we wrap things up here in the next 4 or 5 minutes.
Sure. So there's a question about facilities that already have a tight limit and might be getting by with chemicals. How can they experiment with biological processes without, incurring risk of violating that limit?
That's a great question, and I'll tell you, there's state to state, there's a lot of difference of ability, I guess, of the regulators to be flexible. I know that Tennessee, for example, would very much like to see people migrate off of chemicals to go biological, and I suspect if it's a Tennessee plant, you could talk to your regulator, tell them what you plan to do, and you would get support. I'll tell you, in the state of Montana, they have something, I forgot what they call it, but the state will write a letter, which is you give them a plan and they'll write a letter, and that letter will help you with third-party actions. If any environmental group wants to go after you, the state will go on record and saying, as long as you're making an effort, we support your effort, and if you have some temporary excursions, we're with you because it's leading long-term. What's more sustainable, biological or digging chemicals out of the earth and putting them into our treatment plant? So it's really up to your regulator. And if you have a good relationship and that regulator has the flexibility, then you may have some ability to experiment. There are other states, and I'm not going to name them, that I'm aware of that would not be willing to support that whatsoever, and would actually intensify their enforcement observation if you tried to make the change. So it's really between you and your regulator. It's a fabulous question, and if I were king, I could give you a different answer, but I'm not. And it's a good thing I'm not.
I was going to say it's time to have that election, but one last question, Peter, if we can indulge one more. If we have time for that.
No, we can probably do a couple more. It's fine.
Okay. How do you determine how often to turn off the aerators in an oxidation basin to get nitrogen removal?
You start slow, okay? My advice is like start with an hour. You turn things off for an hour, you get used to it. It's not just a change in the biology that's getting used to it, it's the treatment plant staff. You need to get used to being able to walk by and see everything with the air off, and it's pretty freaky if you've never done it before. My guru for all things microbiological is a fellow named Michael Girardi, Gerardi, Michael H. Girardi. He's written like 10 books. If you're in need, go to one of his, look for Microbiology of Wastewater book. He says tells me that nitrifiers, the bacteria that will remove ammonia, can live up to 24 hours without air. So you don't need to worry about the bacteria surviving it. So just start out slow. And if you turn the air off for an hour, really nothing's going to happen. Then you turn it off for an hour in the morning, an hour in the afternoon. Probably nothing's going to happen, but you're almost saving 10% electricity. Then you can start extending that. Extend it by half an hour at a time. And you can get up to 2, 3, even 4 hours of air off time in many situations. Other situations, you can't have the air off that long. And in fact, I'm going to get into that a little bit on the SBRs, because that's a process control strategy, making sure that those air off cycles aren't too long. And we'll talk about that next month in that one.
I'll jump in with one question here. I don't know, I didn't hear if you asked this one already, Brendan. Excuse me if you did. What is the optimal dissolved oxygen level to maintain in the anoxic zone to provide the ideal nutrient removal?
As low as possible. And if you have a DO of, so the ideal would be you can't detect a DO. The ideal would be, I like to see an ORP of about a -100. I've seen cases where they work very well with the DO of getting close to even half apart and an ORP of positive 100 plus. But more often than not, a DO is close to 0 or at 0 and an ORP in the negative territory. It's generally what I find to be the optimum. Everyone's a case-by-case basis, but that's a good starting place.
Great. I think let's finish it up with one more question, Brendan, if you have it.
Sure. Is it better to turn aerators off for multiple hours at a time once a day, or for shorter times multiple times a day?
It's better to have them off for an extended period of time. And the big driver for me is what's too long? Too long is if your mixed liquor in your aeration zone starts to drop, then you're parking too many solids, and that's not good. The other way is they're off too long is if you start to see that release. You start to see too much ammonia, it's overwhelming it. You start to see too much phosphorus release. But what we're trying to do is create an environment, and there's a transition period, right? From when you turn the mixer off and the solids start to settle. It's only after some settling occurs that it really starts to develop into septic. Another way of having them off too long is if you kick them on and it creates too much odors, then that's obviously too long being off as well. You'll get the odors when it turns back on. That's when you get the odors. It resuspends the material from the bottom. So there's some guidelines there. Hopefully those are helpful. I just want to thank everybody. We've still got 600 people hanging in there, just incredible. I thank you for your interest, and I just hope the majority of you will tune in next month. And like I said, for the government participants, I'm really looking forward for the 4th session. Encourage you strongly to attend that. Thanks again.
I want to also thank you, Grant and Brendan and Laura, for all the help putting this on today. And thank everybody, all the attendees, for hanging in there for the extra time that Grant afforded us, and really appreciate it. I think things went great. Thank you. And I'll leave the webinar open just for about 5 minutes if you need to download anything. Otherwise, the recording will be turned off. But thank you and have a good rest of the day.